Imagine pouring champagne into the top glass of a pyramid. When it overflows, it splits perfectly left and right. Sounds simple, right? Now what if I ask you, after pouring 100 million cups, how full is one specific glass? 33 rows down? That's today's problem, and it's a beautiful dynamic programming pattern. We're solving 799 Champagne Tower. This is a dynamic programming simulation DP problem. What's happening? Glasses are stacked like a pyramid. Each glass holds 1 cup maximum. Extra champagne splits evenly. Half goes left, half goes right. We're given poured, query row, and query glass, and we must return how full that specific glass is between 0 and 1. Constraints: 0, less than or equal to, poured, less than or equal to 10 to the 9th. Query row is less than 100. Important detail: maximum 100 rows. That's a huge hint. This is dynamic programming. Let's simulate small examples first. Example 1. Input: poured equals 1. Query row equals 1. Query glass equals 1. We pour 1 cup into the top. The top glass holds exactly 1. No overflow. Second row, empty. Answer equals 0.0. Example 2. Poured equals 2. Top gets 1. 1 cup overflows. Overflow splits. 0.5 left. 0.5 right. So the second row glasses. 0.5. 0.5. Querying row 1, glass 1. 0.5. Example 3. This one is mental visualization. Poured equals 4. Top, 1 stays. 3 overflow. Each child gets 1.5. Now each child keeps 1. Overflows 0.5. That overflow goes to the third row. You start seeing a pattern. Every glass only cares about overflow from above. That's the key. Each glass can hold maximum 1. Only passes down. Overflow. Overflow equals open parenthesis amount minus 1 close parenthesis divided by 2. This screams row by row dynamic programming. We create a 2-dimensional triangle. DP bracket row bracket column initialize DP00 equals poured. For every glass, overflow equals max of 0 and DP are C minus 1. DP are plus 1C plus equals overflow divided by 2. DP are plus 1C plus 1 plus equals overflow divided by 2. Complexity: rows maximum equals 100. Total cells approximately 5,000. Time complexity: O of 100 squared. Totally safe. Now here's the clever part. We don't need the whole triangle. Why? Because each row depends only on the previous row. So we store just 1 row. Now let's walk through the optimized solution. We create a single array called row. The size is query row plus 2. Why plus 2? To safely handle the rightmost overflow. We initialize row 0 equals poured. Then we build the tower row by row. For each row we traverse backwards. Why backwards? Because we don't want to overwrite values that are still needed for computation. For each glass C, overflow equals max of 0 and row C minus 1 divided by 2. We replace row C with the overflow amount. That represents what flows downward. Then we add that same overflow to row C plus 1. After processing up to query row, the answer is simply the minimum of 1 and row at query glass. Because no glass can ever hold more than 1. Elegant, efficient, classic dynamic programming. Why query row plus 2? We need extra space for right side overflow. Why iterate backwards? This is crucial. If we go left to right, we overwrite values before using them. Going right to left lets us update in place. This is classic space optimized dynamic programming. What does this line do? Overflow equals max of 0 and row C minus 1 divided by 2. If the glass has at most 1, no overflow. If it has more than 1, the extra splits evenly. Why return minimum of 1? And row at query glass? Because the question asks, how full is the glass? Even if DP stores 1.7, a glass can only be 1 full. Common mistakes. Forgetting to clamp result to 1. Iterating forward instead of backward. Using integers instead of floats. Or building the full 100 by 100 DP. Why this is DP? Simulation DP, a state transition problem. With row-based dependency. Pattern to remember. When state depends only on the previous layer. Use a one-dimensional rolling array. Seen in Pascal's triangle. Triangle path sum. And knapsack optimizations. Complexity. Time. O of query row squared. 10. 0, 0, 0 max. Space. O of query row. Extremely efficient. Even if poured equals 10 to the 9th. We don't simulate liquid. Only the overflow structure. Lessons. Controlled simulation. Overflow propagation. Space optimized DP. And backward iteration trick. Looks physics-based, but it's pure dynamic programming. If this explanation made it click for you, hit like. Subscribe for clean, dynamic programming breakdowns. Comment, 2D or 1D DP? Which approach do you prefer?